Bismillahirrahmanirrahim. Dear students, Assalamu alaikum. In this video lecture, we are going to discuss thoroughly the concept of reciprocal space in crystallography. Once we speak of space, we always refer to some physical quantity. Like we can speak of energy space, momentum space, and the normal XYZ space, right? So in all these spaces we can describe a line, we can define an area, we can define a volume, etc. Once we invert the values of x, y and z and plot all these values, then we can get a reciprocal space. So this concept is something like that. As far as this very notion in crystallography is concerned, we always define this reciprocal space in transmission electron microscopy. And remember, this concept of reciprocal space is something real. This is not imaginary. And this constitutes an important atmosphere, an important section of electron diffraction patterns in transmission electron microscopy. So I can read these sentences and then we can interpret it. Reciprocal lattice is something fundamental to solid state physics because it greatly facilitates the description of periodic structures. Remember that Gauss's law is the consequence of the periodicity of the space lattice. So it's like the periodic structure which is also described in reciprocal space. So it's used to describe extra diffraction from periodic structures. Here we choose to start out with a formal definition and description of some mathematical properties. Okay, we have already discussed the concept of space lattices or direct space in face-to-face classroom situations. To define a direct space or direct lattice, we always choose some lattice parameters, like you can say A, B and C in three different directions. And remember, these three different directions are called crystallographic axes, and these directions, these axes may not be perpendicular to each other like the ones in Cartesian coordinate system. So likewise we can define a reciprocal space and a reciprocal space lattice with the help of some basic vectors defined in here as B1, B2 and B3. In some books these notations are A steric, B steric and C steric. So you should not be confused with these notations, right? We have a mathematical representation linking the direct lattice vectors and the reciprocal lattice vectors. So B1 is linked up with the reciprocal with the direct lattice vectors in this way. Okay, this is A2 cross A3 divided by A1 dot A2 cross A3, and this is multiplied with the 2 pi, and 2 pi is nothing. This is a factor which defines that by rotating an object or the situation by 360 degree, so we can get the similar situation. So this defines like that. Okay. So and this a1 dot a2 cross a3 in denominator defines the volume of the basic unit cell in the reciprocal space. Okay. Similarly, we can define b2 as 2 pi into a3 cross a1 divided by a1 dot a2 cross a3. So this is again a volume. So the volume appears in all of these equations. So you need just to focus on this numerator. So when b2 appears, this is the second place, right? So b2 appears on the second place, so we don't have a second place vector in the numerator. So this is just a simple logic to remember these equations. Similarly, for b3, we don't have any a3 in here, and similarly for b1 we don't have any a1 in here, right? The rest of the things are similar. So now you need to understand the physical significance of these equations. So in the reciprocal lattice, sets of parallel atomic planes are represented by a single point located a distance 1 over d hkl from the lattice origin. Okay, I'm telling you very important thing about the reciprocal lattice. Once you get electron diffraction or neutron diffraction data, okay, whether in the form of peaks or in the form of spots, okay, so this is basically reciprocal space. This is reciprocal space. This is nothing. Now crystallographers then considered this lattice and thought how to construct this sort of space mathematically based on simple logic. Okay, so we can construct theoretically, mathematically this reciprocal space, and then we can compare it with the one obtained experimentally in transmission electron microscope. Okay, I will show you my own data which I myself got in a laboratory in Sheffield, some electron diffraction patterns. So I will show you after this slide. The mathematics of the reciprocal lattice construction is simple vector algebra. In real space or direct space, we can define any lattice vector Rn by the equation. This is n1a plus n2b plus n3c. So this is that simple equation that we normally come across while discussing crystal lattices. Okay, so n1, n2 and n3 they are integers, and a, b and c are the basic lattice parameters that are defined in a crystal lattice. Right. So any reciprocal lattice vector which is represented by r steric can be defined in a similar manner, like the form of the equation in here. So we can set another equation in the similar form, which is m1 a steric plus m2 b steric plus m3 c steric, where these three a steric, b steric and c steric are the unit cells translations in reciprocal space, and m1, m2 and m3 are all integers. So in here we define the reciprocal lattice vectors with the help of steric, okay, instead of b1, b2 and b3. So I purposely introduced both of the symbols for you so that you may be familiar with that. So the directions of these new vectors are defined by the relations Now this set of equations defines a very fundamental relationship between A steric, B steric, C steric, and A, B, C. Okay, remember, A, B, and C are direct lattice vectors, whereas A steric, B steric, and C steric are reciprocal lattice vectors. So by taking a dot product of the first reciprocal lattice vector with that of second direct lattice vector, and similarly like that, the positions of both the vectors are different than numeric positions. Okay, so with this sort of setting we will always get a null result, right? So in words we can say that A steric is normal to both B and C. Okay, because A steric dot B and A steric dot C, this gives us a null result. So we define the lengths of these vectors by another set of relations. So once we consider the dot product between the direct lattice vector and the reciprocal lattice vector of similar places, similar positions, like A steric and A, B steric and B, C steric and C, then we will get a unity. Now let's define why we get this unity. Is this because they make an angle of 0? Is this the reason? No, this is not the reason. So let's read this text. This equation uniquely defines the length of the vector A steric in terms of the length of the vector A. Therefore, these equations give the scale or dimension of the reciprocal lattice. So the product of the projection of A steric on the vector A multiplied by the length of A is unity. So as I told you, this result doesn't mean in any way that A steric is parallel to A. They don't make 0-degree angle with each other, right? So this is the combination of this dot product is managed, is arranged such that we can get a unity. So the direction of A steric is actually completely defined by equation 1. It is perpendicular to both B and C and must therefore be the normal to the plane containing B and C. So hopefully you have got the idea of these two sets of equations. Okay, this is very important to understand. Now let's push this topic forward, and we can now see electron diffraction patterns. These are the patterns that were obtained at the University of Sheffield, United Kingdom. This electron diffraction pattern was taken along direction 0, 0, 1, and this symbol, right, means that we have a family of directions. Okay, this P is for pseudo-cubic. You don't focus on this much because this is not a matter of concern for you people at this level. So this is 1, 0, 0 direction and a general direction again, and this is 1, 1, 1 direction. Okay, so we have two sets of electron diffraction spots. Major spots like the ones you see in here, major spots. Okay, and then minor spots. Some minor spots can be easily seen between two adjacent major spots in horizontal rows. Okay, and the most intense and bright spot in the center. So this is the direct passage of the beam. So this is electron diffraction pattern. So this is the direct passage of electron diffraction, the electron beam that's passed directly through the crystal undiffracted. So from directly I mean undiffracted. Okay, so we can see similar spot in here. Okay, so this is undiffracted spot, and this is the indexation. Again, you don't be concerned about these indexation. This is means half, odd, odd, even, half, odd, odd, even, and quarter, 0, 0, 1. Okay, this is just the indexation of these minor spots. So every major spot like these, every major spot represents a family of planes, a family of planes in that particular crystal. Okay, now as I told you, reciprocal space is something real which you saw in this slide. This is reciprocal space. Now we can construct this reciprocal space or this sort of reciprocal space on the basis of very simple logic. Okay, this is a very simple crystal lattice. In this crystal lattice we have infinite number of choices to define planes and to define lattice translational vectors, to define unit cells, to define planes. We have infinite number of choices. So we can consider some planes and of course families of planes. First consider this orange color. Okay, so this is one plane, this is another plane, and then full set of planes. Now as I told you, the interplanar spacing, that is the spacing between two adjacent planes, is D. Right, now we can consider another set of planes, the purple. Okay, so we have many planes that are parallel to each other, constituting a separate family. And so we have interplanar spacing, which is in here and which is also represented in here. So we have another set of planes. Okay, so this cyan color represents another family of planes with this interplanar spacing, the D spacing, and we can consider this set of planes, right? And in here this represents like the one in here, so this represents interplanar spacing. So this is the first step to define and to construct a reciprocal space mathematically or theoretically. So all these things they mean interplanar spacing measured at 90-degree angle to the planes, and of course they should be measured at 90-degree angle. Now this is a real lattice, and this is the construction of reciprocal lattice that is measured, that is constructed from this real lattice. So let us see how it's done. So this is one set of planes, okay, and this is the perpendicular direction, okay, this is the origin. To construct a reciprocal space, we must first define a point as our origin. So this is the very initial step to start defining, constructing a reciprocal space or reciprocal lattice. So this is the origin. So this is the origin, and we have we have in here this in this direction, which is the perpendicular direction to these planes. We always take the reciprocal of the interplanar spacing. So after taking the reciprocal of this interplanar spacing in the perpendicular direction from the origin, we can always define that. So this is like 0 1, okay, because this is 0 1 planes. And so as I told you, one spot in reciprocal space always gives you a family of planes in the real lattice, okay. So this one spot is obtained by taking the reciprocal of interplanar spacing of this set of planes and in the perpendicular direction. So we have obtained that. Now this is another set of planes. This is very beautiful manifestation, very beautiful demonstration to define reciprocal space. So in this family of planes, again an interplanar spacing is defined in here, and then the reciprocal of this interplanar spacing is taken from this origin, and the value so obtained is plotted in here, such that this direction is perpendicular to this set of planes. And because this is 1 1 set of planes, and why 1 1 set of planes? Because as you know, if we take this as the origin, then this plane cuts this a-axis is in here, it's defined in here, this a-axis and this b-axis exactly upon 1 unit length distance, okay. So that's why this is 1 1 plane and in 2 dimensions. And so we have got only one spot in here instead of the planes, and this is indexed as 1 1, right? So quite interesting. So let's go to the next phase. What does it say? So another set of planes, and again very interesting. So we have got 2 1 planes. And why 2 1 planes? Because you know, by taking this just 1 unit length, the 1 unit cell in 2 dimensions, and considering this plane, then we can say that this is a midpoint, which is half, and this is of course the intercept, and this is 1 intercept, this is upon B and this is upon A. So by taking reciprocal of these intercepts, we got 2 1. So that's why this is indexed as 2 1. Now in terms of reciprocal space, we have taken the reciprocal of this interplanar spacing, and we have gone in the perpendicular direction from the origin, and we have got in here. So this part is basically 2 1, representing this whole set of planes, and which is written in here as well. This is 1 over d 2 1. So hopefully that's clear to you. And this is the new set of planes, right? And because the planes are indexed as 3 1 for obvious reason, in here this is the 1/3 portion of this a-axis, and this is the one whole unit length distance. That's why the reciprocal gives 3 1. And by taking 1 over d 3 1 and going in the normal direction of this set of planes, we have got in here. So this is 3 1. Now gradually we are constructing, reciprocal planes in terms of spots, right? So so this is another set of planes, which is 0 2, and because the interplanar spacing is reduced, so the reciprocal of this reduced interplanar spacing will give us an increased value, which is in here in the form of spot. This is 0 2. So again another this is 3 2, and so on. So we can define many planes like that. And remember, we can go exactly in the opposite directions of this origin. Like in the very opposite direction, we will have 0 1 bar and 0 2 bar. Similarly, we will have 1 bar 1 bar. In the opposite direction, we will have 2 bar 1 bar in the opposite direction, and so on. Okay, so we can construct a similar pattern exactly on the other side of the origin as well. So hopefully you are clear until now. And as we can define a vector, as you saw, a general vector which is the admixture of A steric, B steric and C steric by G. Okay, like the word G is written in here, and this vector, this G, is always perpendicular to the HKL plane, as you saw, like in here. Look, this 0 1 is a G vector which is perpendicular to this 0 1 planes. This 0 2 is another G vector perpendicular to this set of planes. This 1 2 is another G vector which is perpendicular to this set of planes 1 2. So generally we can say that if we have a vector G, okay, so this G vector will be perpendicular to its corresponding HKL planes. So this is a diagram showing this idea to you in another way round. Okay, this is an HKL plane like the one shown in here. It's arrowed. Okay, HKL. So this OA gives you its H index, OB is its K index, and OC gives you the corresponding L index. Okay, and so this is HKL, and from this origin to the center of the plane. The center of the plane is represented by n. So this ON is the vector which is perpendicular to this HKL plane. Then this is quite clear from this diagram. So it means that this ON is parallel to G. So this means like that. Let's read this text for you. This caption reads, the plane ABC has Miller indices HKL. The vectors OA, OB and OC have lengths A over H, B over K and C over L. So this is quite clear. So these are the lengths now, not Miller indices. Okay, so the lengths could be obtained with the help of this B by K, A by H. So this is like inverting the reciprocals, inverting the HKL indices. Okay, and then you can get intercepts. So the vector ON, which may be written as N, is normal to the plane HKL as I stated. So the reflection G associated with diffraction from the HKL planes is parallel to N and normal to all vectors in HKL. So hopefully you have got the idea of reciprocal space and the G vector and its association, its linkage with the direct space vectors. You please stay tuned for my other lectures that will follow soon, and for now, Allah Hafiz, God bless you.